In this video, we're going to be exploring a little bit more in-depth complex synthesis. So this is going to be our first real dive into chemical synthesis. So because we now have reactions from nucleophilic substitution, we have elimination reactions, and we have addition reactions to alkenes, we can start putting them together and building more and more complex molecules. So let's start examining how we would approach these problems and then tackle a few of our own. So one potential problem we could have is turning cyclohexanol into cyclohexane. So our first observation is we go from an alcohol to an alkane. And my first question is, do I know any one-step reactions to take an alcohol to an alkane? And off the top of my head, I can't think of any one-step solutions to this problem. So we're already looking at a multi-step synthesis. So my goal is to somehow go from alcohol to something, to maybe something else, to maybe something else, to an alkane. And I want to do this in as few steps as possible. So I want to find intermediates to get me from alcohol to alkane. And off the top of my head, now we've already established I don't know anything from alcohol to alkane. But I do know how to get from an alcohol to an alkene, and I do know how to get from an alkene to an alkane. So alcohol to an alkene is going to be dehydration, and alkene to an alkane is going to be hydrogenation. So we can do this in two steps. So our first step would be dehydration, which is going to acid catalyzed dehydration, which is addition of H2SO4 or H3PO4. So either one of these would work. That will leave us with the cyclohexene. And then finally, we can do the hydrogenation with H2 on platinum or palladium on carbon to get from cyclohexene to cyclohexane. So we can do this in two steps. So this is the way we want to think about synthesis. We want to see, first off, can we do it in one step? And if we can't do it in one step, what intermediates along the way can get us closer and closer to our end goal product? So let's look at another one. So let's look at tert-butyl alcohol to this substituted alcohol with bromide. So off the bat, our net transformation is we've added Br terminally. Now I don't know any reaction off the top of my head that can just add a Br to a terminal carbon, but we do notice this functionality here. So we have a Br next to an OH, so this is a vicinal arrangement. And this is what we call the halohydrin. And halohydrins we know how to form. Halohydrins are going to be an alkene plus, X2 in H2O. So that means this species came from an alkene. And if we're thinking about the alkene that this came from, it's going to come from this 2-methyl 2-methyl-1-propene, excuse me. So adding, doing a halohydrin formation from 2-methyl-1-propene, so we would add Br2 and H2O, would get us to this final product. But how do we get from this alcohol to this alkene? And we can do this in the same way we saw this in the previous problem. Alcohol to an alkene is going to be a dehydration. We've lost OH, we've lost an H terminally, so this is going to be a dehydration. We can do that by addition of H2SO4 or H3PO4. Either one of those would work. So to go from tert-butyl alcohol to this bromo-substituted tert-butyl alcohol, we first do the dehydration with H2SO4, and then finally, to form the halohydrin, we do Br2 addition in H2O. So let's look at one more example, and then let's try a couple problems on our own. So another example we can imagine, say we go from this 2-bromopropane to 1-bromopropane. Again, it looks like we're moving a bromine over from one carbon to the one next to it. And a good way to do this is to go through an alkene. So if we see a bromine, if we see a substituent move, if a substituent moves, this is a tip-off that we're going through an alkene. So this probably came from this type of alkene, so propene, 1-propene. So how do we connect these dots now? So we can go from 2-bromopropane to 1-propene to 1-bromopropane. So to go from two bromopropane to one bromopropene, we're doing this looks like an elimination reaction, so we're going to add strong base. So this could be something, any number of possible options. So NaOH, this could be NaOMe, this could be NaOET. Any of these would work. And this would do the elimination to form the alkene. Now to go from the alkene to the Br, it looks like we've done an HBr addition across the double bond. So if we do HBr addition, this will take us to the 1-bromopropane. However, if we actually examine this for a second, HBr addition to 1-bromopropane will do Markovnikov addition of Br to the alkene, which would be this position here. We're looking for the anti-Markovnikov addition of HBr to the alkene. So to force anti-Markovnikov addition of Br, we're going to do this in peroxides. So ROR, or you could write peroxides. And that will force the anti-Markovnikov addition of Br across the alkene. So thinking about synthesis, it's important to think, how can we go through intermediates to get from one step to another? So I'm going to put 3 problems up, and if you want to pause and maybe work on them, and then we will go over them. There's, again, as we see with synthesis, there's usually more than one answer. So I'll try and address a couple different answers if there are possible answers for each one, and then show you what I would do. So here's the first one. So we go from 1-butene to this epoxide here. Okay, so that's 1. 2 is going to be this methyl cyclohexene to this cyano substituted, this nitrile substituted methylhexene. And the final one is going to be this reagent here, transformed to this azide functionalized reagent. So if you want to pause here and work on these problems, and then unpause and we will go over the answers. So let's start talking about these 3 problems. Let's start with the first one. In fact, I will let's clear the other 2 off the board so we can talk about them one by one. So let's talk about this first one. So what we've done here is we've let's take inventory of what's happened. We've lost the alkene, and we've formed an epoxide. And it looks like the stereochemistry on this epoxide is trans. So it's a trans epoxide. And it looks like it's on carbon 2 in butane. So my gut reaction would say, okay, where does this epoxide come from? We know one reaction form epoxides, and that's the oxidation of alkenes. So let's draw what alkene this came from. So if we look, we see that the methyl groups are trans to one another, so they will be trans in the original alkene as well. So we come from a trans alkene, okay? And we can close this loop by saying we do the epoxidation with a peroxy acid, so I'll just write MCPPA. Okay? Now what have we done? We've seemed to have taken this double bond and moved it interior. So we've gone from a terminal double bond to an interior double bond. I don't know any reaction to do that off the top of my head, but what that kind of signals to me is that, we know how to make alkenes. The major way we know how to make alkenes is by elimination reactions. So this elimination reaction came from something at this position here, or if we track backwards, it came from something at this position here. So now it becomes a little more clear that we must have done some kind of addition reaction to this alkene, and then done an elimination reaction to get the internal alkene. So if we look, this comes from some substituted derivative of this alkene, and then we're going to do an elimination reaction to form the transalkene. Now I have a choice of what I can choose to add to this double bond. I want it, what I want is a good leaving group so it can do the elimination reaction. So I wouldn't add something like OH unless I want to add an extra step. So I would add something, say Br or Cl. So if we look, the Cl, we'll do HCl. The Cl has been added Markovnikov, so we can simply do HCl addition of to this alkene to form the secondary chloroalkane. We're then going to do the elimination reaction, and this can be done with a whole host of reagents. This can be done with NaOH. This can be done with NaOMe. In this case, I would specify heat. In general, it's good to specify heat when we do elimination reaction, just to make sure we don't do the competing substitution reaction that can compete with elimination reaction. So NaOH, NaOMe, say NaOMe and methanol, and heat will force the internal alkane to form. Remember, Zaitsev's product will tell us it will form the internal trans alkene preferentially, and then MCPBA would epoxidize this. So our steps would be, we do HCl, then we do NaOMe and heat, and then finally we do MCPBA, and that would be the solution I would give for this problem. So let's look at the second problem. So the second problem was taking this methyl cyclohexene and converting it into the cyano, substituted methyl cyclohexene. Now this is a bit more complicated. It seems like we've added a cyano, but we haven't lost the alkene. So it's on the surface, it looks like a bit more of a complicated problem. But let's using the reactions we know, let's try and figure out what it's exactly asking. So first off, my gut reaction is going to say, we have a cyano group. I don't really know how to put a cyano group here, except by nucleophilic substitution. You know, I can add NaCN to a good leaving group, and that'll do nucleophilic substitution to form a nitrile. So that means at this position, there's probably some kind of nucleophilic substitution done here. So that means I want to get a leaving group installed at this position or this position here, such that I can do nucleophilic substitution. So let's play that out. So, okay, let's install a leaving group here. So let's say I want to do HBr, but this is the anti-Markovnikov position. So that means I have to do this with peroxides. Okay, so I've done Br addition, and I'll ignore stereochem for a second, because the peroxide addition will scramble stereochem. Okay, so we have a Br, and then we simply add NaCN, and say we do this in DMSO, and that will leave us with the nitrile substituted methyl cyclohexane. But now we're stuck because we've lost this alkene. So what this tells me is not only did we do a substitution, but we also had an elimination reaction that puts this double bond here. So what we need to do is not only install one, but we need to install two functionalities across this double bond. So a way to install two functionalities is with addition of X2. So let's say we add Br2. Okay, so, and I will draw stereochemistry here. So we have Br, and again, this forms the enantiomer. Okay, and now what we want to do, we have a choice. We can do the elimination or the substitution reaction. Elimination will not really proceed in the way we want it to, because our bromos are anti to one another right now, so the anti-periplanar configuration cannot be achieved. So it'll probably form an unwanted alkene, like something like out here or out here. So we don't want that. So we need to do the substitution first. And we're going to do a substitution with NaCN, and this could be in DMSO or acetone or DMF. And if we're worried about substitution happening at both positions, we have a tertiary alkyl bromide and a secondary alkyl bromide. The secondary alkyl bromide is much more prone to what was an SN2 substitution here. Remember, SN2 doesn't really happen at tertiary centers because it can't do that backside attack. So we're going to have substitution at the secondary alkyl bromide, the secondary bromo position, and that will be reverse the stereochemistry. And finally, we can do elimination. And if we look, we now have a Br and an H that are anti-periplanar to one another, so we can do the elimination that will generate this alkene here. And this can be done with, I'll just do NaOMe and methanol and heat, and that will eliminate the bromo and leave us with the substituted, tetrasubstituted alkene that we have and which is desired here. So again, we do Br2 to install the dibromo. We'd have the substitution, and then we do the elimination. An alternative way you could do this is you could, instead of doing Br2, you could do Br2 and H2O, form the halohydrin, and I'll draw stereochemistry here. And then we do the substitution. So this step is the same. We do the substitution at the bromo. Now there's no risk of having substitution at the OH because the OH is a bad leaving group. So that will not do substitution. You run no risk of competing reactions. And then finally, you could do, to form the alkene, you could do something like a dehydration to form the tetrasubstitute alkene, the same product that we saw above. So either of these routes would be equally likely or equally work the same. So let's look at the third example. So the third example also has a couple different routes, and it's probably the most challenging to see right off the bat. So we had, let's see, we have this reagent transformed into this azide. So as we saw with azides, the only way we really know how to synthesize these is with substitution. So this came from something that looked like this, like a good leaving group, and we added NaN3 to it. So we've added NaN3. So how do we get this from our starting material? And it looks like, you know, what we've seen now is we can walk double bonds by doing addition reactions, elimination, addition reactions, elimination. So what it looks like, so we've done an addition reaction, eliminated, then done another addition reaction. So this comes from this alkene here, because that's the only alkene this can come from. I will specify this X now. So we have to do terminal X addition, which would be anti-Markovnikov addition to this double bond. So to specify anti-Markovnikov addition to a double bond, we would do something like HBr and peroxides, and that would add Br to the terminal position of the double bond. Now, how do we walk this double bond out? This is going to come from an intermediate where we have a substituent, similar to the last reaction. We have a substituent on the secondary position. So we've done, this is again, an anti-Markovnikov addition. We can do Br as well. So we're going to do the same thing, HBr and ROR. And then this is the key step here. We want to do an elimination, but not form the Zaitsev product. We're forming the Hofmann product. So if we remember, to form the Hofmann product, we need a bulky base. We'll do something like potassium terbutoxide, terbutanol. Remember, this here would be the Zaitsev product, and if we force it out, it's going to be the Hofmann product. We want to form the Hofmann product, so we use a bulky base. So this would be the shortest route. Now, you could do this with alcohols and alcohol substitutions, but this would be the route I would do because this would be the shortest. So you do Br addition anti-Markovnikov, for elimination to form the Hofmann product, Br addition again anti-Markovnikov, and then substitution with sodium azide to form the azidoalkane.